Hello, and welcome back. We are going to be discussing design for Six Sigma in today's class. Now, the goal of design for Six Sigma is that as you... Gotta use a marker that's readable. That as you design for a project, you're not just simply designing a product itself, okay? When somebody sits down and thinks up of a ruler, and they want to create a ruler, they're not only coming up with the world's best ruler or the most effective ruler or whatever it is that makes this ruler appealing, they're also coming up with the entire process of what materials are going to make this up. How are we going to take these materials? How are we going to process them? Once we get those materials processed, how are we going to assemble this? Once we assemble this, how are we going to package it? And how is it going to move between all of those stations along the process? Okay, so when we talk about design for Six Sigma, what we're really doing is we're talking about the Six Sigma process and how we can prepare early in the manufacturing process to ensure that the Six Sigma process occurs correctly. So now I've used the word Six Sigma now a few times. I've written it on the board once. What does Six Sigma mean? Okay, well, Six Sigma is the idea that you are going to have errant products. If we go back to our example of the ruler, you may have a ruler where the ruler itself is 12.1 inches long, and maybe that's not acceptable. Maybe it has to be an exact 12 inches with some tolerance. Maybe the desired output is 12 inches plus or minus 0.15, okay? And then as long as the printing gets on there nicely, that's good. And then maybe you want to make sure that the markings get put on there correctly at the correct sizing. Maybe you make sure that the markings don't rub off with a certain thing. So markings are correct size. Markings stay put, they don't rub off. And then maybe we make sure that there are no sharp edges. Okay, no danger points on this ruler. All right, so this is what we're going to put as our requirements for our ruler. Now we can always keep going. There's a lot of other things you don't want to have on a ruler, like you don't want it to be warped, you want the edges to be straight, all of these things, and you can define what tolerancing you put on there for as far as straight edge goes. But for now, we're just going to focus on these three things. Actually, instead of this, I'm going to have this be actually. And we're going to say deviates from the edge by a tolerance of 1/1000th of an inch, which is not a whole lot, but we'll say that that's okay. All right, so we're going to focus on these three aspects of design. We could always include no sharp edges, or the sharpness of an edge isn't to exceed a certain value. When we talk about Six Sigma, what we're talking about is how many components that are produced fail the quality. Requirements. Okay? And this is what you really want to know. In Six Sigma, what you're looking at is you have the total cost for manufacturing, and then the number of the total number of parts that lie in an error. Okay, if you have, I think it's like 60% of your parts are good. What that is, oh, it's 30% of your parts are good, but 60%, well, 70% are bad. That falls within the 1 sigma category. It means you're producing 2 parts, or you're producing 3 parts, and of those 3 parts, 1 of them is good. Okay, your total cost is enormous because you have to produce 3 parts to make 1 good part. And then you have to spend time shifting them out, and what do you do with the waste parts? All of that. Okay, but now when you look at 2 sigma, now things are flipped. For every 3 parts, 2 of them are good. This is approximately 70% of all of your parts are good. Okay, and now your costs are going to decrease substantially. Now, as we keep moving forward, let's say the total number of parts that are actually good continues to increase. So now we're at about 80, 90%. 90% is about 3 sigma. Okay, at about 90%, your costs are continuing to increase, to decrease, because now out of every 10, 9 of them are good. And you've done a great job of setting up your system so that you only throw 1 part out of every 10. Okay, so again, a 4 sigma, now it's just about 95%, and every 20 parts, 1 of them is bad. Okay, now for some companies, the costs begin to increase because now you have to inspect every single one. You have to have very rigorous means of controlling this quality. Back here where you accidentally produce 1 in every 3 that's good, you didn't have to put a whole lot into manufacturing. You didn't have to put a whole lot into tolerances. You can just chop things up and drop drill bits, and things are great. But as we move forward along the error, as the number of errant parts, your total costs decrease because you have to make fewer parts, but then it starts increasing again because you have to increase the rigor by which each part is made. Okay, so we get to now 4 sigma. 4 sigma for a lot of companies, 95%, 1 in 20, that's going to cause the cost to go up. 5 sigma, you're now looking at 99%. Okay, that's going to cause the cost to go up substantially. And you may be looking at 6 sigma here. 6 sigma, which you have, it's like 99.99%, 1 in every 10,000 is a failed part. And the cost there is now substantial. So you have this nice parabola where most people say, well, the sweet spot is someplace in between 3 sigma and 4 sigma. And between about between 90% and 95%. Someplace in there, really nice. If we can get 1 or 2 in every 20 to be that are bad that we throw out, we're having a good day. Okay, that is the low cost. This is the sweet spot. Okay, the idea about design for 6 sigma is now we're not going to recognize this point right here. We're going to do what we can to design for that 6 sigma cost actually being the lowest. So that now we have the, if I'm going to draw in blue, the actual current production line. And for cost, if we want to try to minimize the total cost, we're producing at about an error of maybe 93% accurate, 7% error. But now when we look at design for 6 sigma, the goal here is we want this to be the lowest point, where 1 in every 10,000 parts is errant, or 1 in every million parts is errant, okay? Rather than having 1 in every 1,000 parts errant. Now, why would we want this to happen? Well, we have a number of reasons for this. Okay, first of all, there's less waste. We live in a world where we try to be more conscientious of the waste products that we're producing. If we are more conscientious, the waste products we're producing less waste. It means we're better utilizing our materials, which is a great way to be a designer. Okay. Second, less time. If 1 in every 10,000 parts is bad, it means you spend less time making bad parts. It's a better usage of your time. It also allows for nicer flows in the facility when a part is that unnatural to occur. Okay? And lastly, a big difference maker for every engineer: cost. We can make this so that it is the most cost effective. Now, in this model existing for most companies, just to be making at this level and then just push themselves up to here, it involves a lot of effort to try to make Six Sigma happen, which increases the costs. But if we design for Six Sigma from the start, we can cut those costs out immediately. Okay, so I'm going to keep my example here on the board, and we're just going to generally talk through what it means to design for Six Sigma. And I might check and see if I have another battery, because I do. I'm about to start cutting out on my video, and makes for very interesting sound effects. But honestly, I like the part where I just keep talking, but I shut off my microphone, so you have no idea what I'm saying anymore. So let's talk about what it means to design for Six Sigma. Okay. Now, the design for Six Sigma process is actually very similar to the engineering design process itself, right? The engineering design process, you start with problem framing, you come up with ideas, you realize those ideas, and then you analyze to determine what improvements can be made, and ultimately to determine whether or not the problem has been solved. Okay, that's the engineering design process. Now, beyond that, what we're going to do for design for Six Sigma is we're actually going to employ this type of a process just in a manufacturing setting. So the 4 steps that are given for design for Six Sigma methodology are, first of all, to identify. Second of all, to design. Third, to optimize. And fourth is to validate. Okay, now this actually partners very well with what I've given you for the engineering design process. As the goal in identifying is identifying what types of errors are the most important to the population. Okay, now here, problem framing for the design process, we're identifying what types of characteristics are most favorable to the population and how we can emphasize those, how we can optimize those, how we can make it better, stronger, more powerful, more fuel efficient item because we recognize the needs of the population. And identify, what we're doing is we're doing very much the same thing. Okay, so for step 1, identify. What we're going to do is we're going to identify what it is that the population wants when they look at our product. What kind of errors are acceptable? What kind of errors are not acceptable? Okay, if you get a ruler and your ruler edge looks like this, that's not kind of acceptable because a lot of people will use rulers as straight edges. Having a straight edge is actually very important. Okay, now on the flip side of it, So this straight edge, very important. On the flip side of it, are the markings the correct size? Do you accidentally have a spacing? Is it off by 0.05 of an inch, which is unheard of for manufacturing tolerance? Is this the case? 1/20 of an inch, is it off? Well, what about if the tolerance it's off by 1/100th of an inch, which is still astronomical in a manufacturing setting. 1/100th of an inch? Well, the more tolerance you give to an object, the cheaper it is to make, because quite frankly, you don't have to employ very specialized technology that can get very precise every time. It does allow for more errors to occur. So the lower the tolerance, the higher the cost is going to be generally. So understanding that, if we can find a way to look at all of our different design requirements, all of our different quality requirements, and say, well, let's increase the tolerance to the maximum value for the things that population aren't going to care that much about. And then let's decrease tolerance, but only for the places that are absolutely critical for the population. Here, having a very straight edge, this is critical. Having a marking is the correct size, probably not as much. Believe it or not, if they're off by 1/100th of an inch, I mean, that's almost not even noticeable. When you take your mark, when you take your pencil and you try to put a mark on a pencil, on a ruler, it's very difficult to get that with 1/100th of an inch accuracy. So if your markings are off by 1/100th of an inch, it may not be that bad. Now, 1/100th of an inch is still a giant tolerance for a manufacturing environment. So we can actually get much better than that. But that's an example here. We don't have to have a super tight tolerance. We don't have to demand that these markings are within 1/10,000th of an inch, which is pretty standard for a lot of quality assurance. We don't have to make sure that happens because the human eye, the human pencil can't even handle that. If we make sure that these are within 1/100th of an inch or 5/1000ths of an inch, that's probably going to be good enough. Okay, but here the straight edge, if it's not straight, that is noticeable. If it varies substantially, that is a problem. So 1/1000th of an inch is not unreasonable there. Okay, but all of that comes in the identify phase. What errors are the least undesirable? Okay, and for those, you increase tolerance. And what errors are most critical? And for those, you increase the tolerance. Again, when we're looking at Six Sigma, the way that we define our standards for quality are going to define how we kick this thing out. If this straight edge varies by 0.02 of an inch, as it currently stands, that straight edge gets kicked out. It's an errant part. It goes into waste. If the markings are the correct size, if we say 0.005 of an inch, if they come in and they're 1/100th of an inch off, it's outside of what is acceptable for the markings distance, and that gets kicked out. It's an errant part. Okay? When it comes to Six Sigma, we want to reduce the number of errant parts. And part of that is by recognizing the quality standards and adjusting the quality standards to be realistic to the customer needs. Okay, so that part is identification. You need to recognize what is it that your machines are capable of doing. Do you need brand new machines? Okay, if you have machines that are capable of producing 10 100,000ths of an inch or 1/100,000th of an inch accuracy, if it's capable of doing that, but it's really slow, maybe you look at a different machine. Or maybe you employ that to monitor your straight edge, if possible. Okay? You want to make sure that your machine tolerances match what you want from your device. It should match what the customers want. And if that isn't the case, you get different machines. You get a machine that's better. Okay? If your marking machine has the worst tolerance, that's okay. Because as we've already said, this is probably the area where the least tolerance is needed. The highest tolerance. So that's the identify phase. The second phase that we jump into now is the design phase. Okay, so here we've done a lot of research, we've gathered information, we've performed studies, we've maybe brought in customers in-house and had extensive discussions with them, usually a very costly process. But that's all going to pay off because it better helps us understand what our quality needs have to be. Okay, so now as we move into the design phase, now what we're doing is we're actually designing for this part to be made. Okay, this is what kind of machines. We're going to order one, we're going to buy one, we're going to produce materials for that machine, we're going to create methods for that machine, we're going to design workflows. This is the actual process of putting together a manufacturing plan to produce a part. Okay? And throughout this process, you're going to be allocating a lot of resources. Do we buy a new machine that's more capable based on our research that we didn't identify? Do we build assembly lines because they're going to help better orient the parts when they go into a machine? Do we order different parts as they come in because they come in with better material properties or higher material quality? This is really the design process. It's really putting together that plan. So once you've done the design work, now you move into realization. Nope, sorry. Optimization. My apologies. For the optimization phase, what we do is we then review. What is it that we designed, we put it together, we're manufacturing parts. Now, what are we doing and how can we make it even better? Okay? We're looking at this and we're saying you're actually gathering data. And that data is going to be useful for establishing how we can progress forward. What you're doing is you may be employing different analytical methods for comparisons. Okay, and you may be spending some time identifying where an error occurs. Okay? And you're spending time understanding more about this process. And then lastly, after you have implemented some changes to optimize the experience, here's where you move on into validation. Okay? In the validation phase, this is basically asserting, here's what we have, here's how we know it. Okay? So here's where you gather data that showcases how many parts are you producing that are errant. Okay? Does it fit in that 6 sigma category? Are you closer to 3 or 4 sigma categories? No. Is that necessary? Is it too stringent? You go out and you actually see how much waste is being produced. How much money is it costing? You're gathering all the data on what the plan that was implemented, what it's actually doing. You're wanting to know here is this is the part where you finalize a lot of your plans. Okay, we state, here's the process that we're going to do. We've already gone through the optimization phase. Here is now what we're going to do to make sure that we are reducing the number of errant parts that we're producing. Okay, this will come up with a lot of communication and that sort of thing, so that we're moving forward proactively in trying to get closer to that Six Sigma error quality. So this is the process of design for Six Sigma. It involves a lot of proactive thinking, a lot of recognition of the manufacturing environment, a lot of thinking about potential errors and what it is that you cannot make mistakes from. We're going to be coming back to Six Sigma later on in the semester because it is a very big portion of the curriculum for manufacturing in today's world, because errant parts are a big piece of cost to a company. But we'll be coming back to this material later on in the semester, so I guess I'll see you then.